And what I want to do in this one is on the one hand build this abstract animation that we use to promote the course, and on the other hand an abstract sculpture of a male head, the same male head that we have worked before. So let's just drop down a geosub and load this up. Just select it here. Again, it's a 3D scan that I downloaded from 3dscans.com. And that comes in like this. So let's drop down a transform, wire this up, highlight it, go to move centroid to origin, and let's scale that along its y-axis and maybe rotate it a bit so it's looking somewhat straighter, like this. Next, let's scatter some points on the surface of this figure. And in order to not scatter it uniformly, let's drop down a color first, a point color, and that's going to be white in our case, and then drop down a paint node, which will allow us to paint in different colors. So in my case, let's set the foreground color to be black, and I have to have this node selected here and have to be in this tool mode here. And what I can do now is with my mouse wheel just increase the brush size and then brush in black areas here. And later I'm gonna use those areas to define how many points will be scattered on them, and white areas will have more points and black areas will have less points. So a bit like that maybe. Let's just revert this. By right-clicking I can select what my left and middle mouse button will do. So in our case, let's just use the middle mouse button to smooth the whole thing. So I can go in and apply this smoothing algorithm here. Smooth out this just a little bit. Okay, now let's drop down a scatter sub and set this up to use color, the diffuse color, to drive how many points will be scattered where. Let's check density attribute and tell the scatter sub to use the color as a density attribute. And as you see here, those areas that I painted black do not contain points currently. Let's dial down the overall point count to say something like 80, like so. And this will be the center points of our cells that will be advected and pushed together around the head. So let's go ahead and create those original bubble seeds by dropping down a sphere, scale that down to say 0.1, turn this into a polygon with a little bit higher frequency, and drop down a copy to points, where we wire in the sphere and those points we just scattered. So this is the seed for our advection geometry. And when I ghost the male sculpture here, I see this geometry is intersecting. That's because the center points are scattered on the surface of the sculpture. Let's move those away a bit. And in our case, let's just duplicate this transform here, increase the scale of the original transform here a bit, highlight this only, like so. And we see now those points have been pushed outside, maybe a bit further. So let's set this to 1.15, like so. Drop down a VDB from polygons, wire in our clone spheres, and dial down the voxel size. Now let's rebuild our advection setup that we've gone over in the previous tutorial by dropping down a solver, wire in our spheres here, and in the solver, first let's drop down a null, just for organizational purpose, call this in, wire up our previous frame input, then drop down a VDB analysis, wire this up, set this to output a gradient, then drop down a VDB smooth, set its filter radius to 2 and its iterations to 2, wire this up in here, and then drop down a VDB advect, where we wire in the original VDB and the field with the gradient that's been blurred that we just created, like so. And while this is ghosted, while the original geometry, the original mesh is still ghosted, let's hit play and see the simulate. Nothing happened. That is because we haven't selected the solver. And this may take a while because now I'm cooking to frame 33, so that's gonna simulate down here. So did I mention this takes a while to solve? So after about 4 minutes we get this, and this is totally not what we'd like to have. On the one hand, we get these artifacts here. On the other hand, the geometry is totally intersecting itself, and also it's intersecting the head. So let's fix that. And in order to fix that, let's dial down the voxel resolution. So in the VDB from polygons, let's increase the actual voxel size. So we have something that simulates a bit quicker, so we can see what's happening here. We can see when the resolution is lower, this actually works quite fine, although it seems like it's intersecting as well, and also it's not regarding the geometry of the head. So let's take care of the head's geometry first by dropping down another VDB from polygons here and taking the original head geometry and turning that into a VDB SDF as well, like this. And then pipe this VDB that we just created from the original head into the second port on our solver. And the second port on our solver is here, so let's use that. And before we go into the VDB analysis sub that turns the SDF, the signed distance field, into the gradient that actually tells the advect node where to move the surface to, let's use a VDB combine to combine this stream that we already have with the spheres and the stream that's coming in through input 2, so the head geometry. And let's set this up to do an SDF union. And when you highlight this, it will give you this. So it'll generate a volume where the head geometry is contained as well as the spheres. So when calculating the resulting gradient, the spheres will be advected away from this head SDF. Let's try that by highlighting the VDB advect, diving up one level, highlighting the solver, and hitting play. We can see now that our head volume is not intersected by those spheres. And also what we could do in order to get rid of those really close distances between all those bubbles that seem to intersect themselves at a later stage of the simulation, let's use the VDB reshape we've been talking about. Reshape SDF, that is. And before going into the VDB analysis, and even before merging this with the head geometry, let's just dilate our spheres. Whoops, that second input doesn't need to go there. Let's just dilate our spheres by 1 voxel, so make them bigger a bit. So what we can see now is those lines where the advected spheres touch stay cleaner now. Okay, let's think about what happened here. In the solver, even before we calculated the gradient from our SDF, what we did is we dilated the geometry, so we kind of inflated it. And what that means is, in contrast to the original geometry, which we're going to advect down here, we calculate the gradients from a slightly bigger geometry. So in essence, what that allows us to take care of is those tiny errors that sum up when you're trying to get the exact gradient on the same voxel that you're trying to advect down here. So that in essence takes care of lots of small advection errors that sum up to those intersecting geometry parts. Let's dial down the voxel size again. Let's say 0.02 up here as well. And let's resimulate this. And let's just try turning this into a surface. Highlight the convert VDB and set it to convert to polygons. And we see, let's just set this to smooth shaded. We get those somewhat decent geometries out there. I think we'll have to tweak there as it's intersecting there. One idea would be to dial in the ISO value, but this in this case has really small values, so we could use that to get this intersecting area a bit clearer. Or let's go back. In the solver, increase the dilation a bit, say 1.5 voxels offset. Let's try resimming that, stop it there, and convert it to a polygon. Which, again, small bug with the volumes, does not display correctly here, so let me just restart Houdini. And we see now it's being displayed correctly. We have a little less intersections here, and I think I could get rid of those with the ISO value parameter in my convert VDB and dial that in. Be happy about this, or maybe also increase the volume resolution. That could help a lot as well. So after a bit of tweaking around, a bit of fiddling around, what in my case did the trick was, the main thing was diving into the solver and within the VDB advect, set all the limiting, all the advection and renormalization steps to the fastest and cheapest computation method there is, which in my case are those settings, so semi-Lagrangian, first order biased gradient, forward Euler, and down here as well. And without going into too much detail about how those algorithms are implemented and used to advect a volume, just by going in here, you see those 2 options, or by going in here, those 3 options, and they usually are ordered by the simplest calculation method, which is executed really quickly, but yields errors if you have a longer simulation or if you need a very detailed simulation. And you have those very accurate algorithms, which take time to calculate. So in my case, choosing the cheapest algorithm actually yielded the best result, and it was, by the way, the quickest. So either way, I could render this either using this poly surface that I did, and by the way, the Convert VDB node also offers this adaptivity slider. So when I have a look at this mesh here, this is really dense because this just stupidly samples the voxels and builds a mesh with kind of a marching cube algorithm, I guess. But when I dial in the adaptivity, we can see that Houdini tries to be clever and intelligently subdivide or remesh this volume so it has more details along sharp creases and corners and less details along areas that have less features, which in the end yields a smaller mesh. Let's just dial this back to 0 for now, and in our case let's just do a quick test render by dropping down environment light, enabling render light geometry, loading an HDRI. Again, when loading an HDRI, make sure you uncheck Show Sequences as one entry and select the proper HDRI. Increase the exposure here a bit and add a camera as well. And in the output context, let's drop down a mantra node and set this in the rendering tab to be a physically based render and dial up the limits to a diffuse limit of, say, 6 and dial down the reflection limits as well. Then make sure my current camera that we created is locked to the viewport so I can move it around and go to my render view, hit render. And you can see, as expected, my meshed advected VDB will be rendered. However, meshing a VDB is sometimes time consuming, sometimes it yields some small errors, and in general it feels kind of clumsy. So is there a better way of rendering volumes and SDFs? And yes, there is. Because what we can do is, on the OBJ level, in the geo object where we have our volume in here, let's just, inside of that, disable the Convert VDB node, dive up one level, and let's try rendering this. And what happens is, Houdini tries to render this as kind of a foggy volume, because that's what volumes originally were meant for. And also, the resolution is kind of really bad, as you can see those blocks appearing here. So in order to let Houdini and Mantra know that we want this volume to be rendered as an isosurface, let's stop this rendering, and on the geometry let's go to Render, Sampling, and add some parameters with the help of the Edit Parameter interface. So let's collapse those, and in the render we only want to add those to the Sampling tab here. So the properties we actually would like to add are called vol, so let's just filter for properties called vol, and within the sampling we get those two parameters, volume isosurface that we drag over here and volume density that we're also dragging over there. Hit apply and accept, and what we can now do here is, on the one hand, dial down the volume density to 0 and check volume isosurface. Go to the render view again and hit render again. And the last thing we need to do is create a material for this volume. So let's just drop down a classic shader here with the standard settings, and in our OBJ level, apply this to our geometry, go to our render view again, and hit render. And as you can see here now, Mantra automatically meshes or automatically generates an isosurface out of this SDF volume, which is quite handy because you don't have to turn it into a polygonal mesh, which takes time and resources. So again, at this point I think it's time for me to tweak all those parameters, maybe paint in different scatter points, experiment with the sizes of the initial spheres, and finally do a bit of shading and lighting to get this to be a nice rendering. So after I recorded the growing bubblehead tutorial, I decided to give this another try and do something more abstract. And basically the setup is really similar to the growing bubblehead setup, so let's go through this. And for that I already prepared some geometry here. Just some background geometry, which is an assortment of boxes, of cylinders, just translated and scaled in the scene and then merged. And the only thing that's left to do is I want to chamfer this box a bit here. So let's drop down a poly bevel here in between, highlight that, maybe after it's transformed. And I want to extrude it, say by 0.075. And now the subdivision is a bit coarse, so let's up the subdivisions to 8, and I want to set the shape to round. So I get this chamfered cube here. Let's highlight the merge node again, and after I merge all this geometry, I turn it into a VDB. like so. A VDB with a rather small voxel size of 0.02. So this is my background, the kind of shapes that my growth will collide with. Now let's build the actual growth. And to do that, I will first drop down a circle to define the area where our growth is starting from. Set that to be a polygon along the ZX plane. Let's maybe ghost this and highlight this here. Ghost the merge node, that's better. That's my circle. Let's increase the subdivs a bit, like so, and also increase the scale. Next, I'll drop down a paint sop. Wire this up, highlight it, and with my gizmo selected, I'll start painting the circle. Not much happening there yet. And of course, I'll have to switch my foreground color to black because my circle is already white. So let's paint this side of the circle black. A bit like so. And I'm aware this is not the most elegant solution for that, but it yields kind of this gradient from black to white. And I'm going to use that in a scatter sop to drive the point distribution by checking density attribute and feeding in the color diffuse. Highlight my scatter sop and I see I've got more points scattered on this side than on this, and that's all I want for now. Let's decrease the total count to, say, something really low like 80. So I got 80 points left here, but increase the relax iterations to something really high, like 320, which is a 4 times over relaxation for 80 points. But it didn't change much here. Let's just highlight the points. And that's an okay distribution to start with. The point of this is just to get some interesting heterogeneous distribution as an initial condition. Let's feed that in a copy to point sop. These are my points, and I want to copy spheres. Spheres with radius of 0.1. Highlight this. And these are my starting spheres. Just gonna set their type to be polygon and increase their frequency to 8. Disable the point mode here, and I can see I've got my spheres scattered on this area now. Next, I'll turn them into a VDB with the help of a VDB from polygon. Again, decrease the voxel size to 0.02, wire this up and highlight it. And I got now my VDB here. Let's move this up a bit. And now I'm going to build the growth algorithm, which is pretty similar to what we've seen in the previous tutorial. So I'm going to drop down a solver, wire up those 2 VDBs, my sources and my colliders, into the solver and dive into it. And I'd like to drop down the VDB advect node first. And I want to advect the incoming geometry from my previous frame, which is this. And I want to advect my geometry with something I'm going to calculate from my incoming geometry, which is coming in through input 2. So I want to calculate the gradient with the VDB analysis and use that to advect my main SDF. But not only do I want to use my previous frame's geometry to generate the gradient here, but I also want to merge it with my colliding geometry. So let's use a VDB combine, which we're going to set to SDF union. So that's like a Boolean union here. And we're going to use the previous frame geometry, that's this, with our collider geometry, and we merge them together. And we're going to feed that into our VDB analysis and highlight the VDB advect. Let's go up 1 level and let this run for a bit. And as you can already see, there are several problems, so let's fix them. On the one hand, we've got these artifacts. On the other hand, those individual cells here intersect, which they should not. Go back into the solver, and in order to prevent the intersection, there are multiple steps which we have to do. First, we're going to dilate our incoming geometry here a bit, using a VDB reshape SDF here. Set it to dilate, and in my case, an offset of 1 worked for me. So what I'm going to do here is before I calculate the gradient, I will expand the geometry. So that prevents these intersections from happening. Because before we calculate the gradient, we already see where those spheres are going to intersect. And when calculating the gradient here of this dilated VDB, we will prevent the gradient to point in this direction. So we will prevent the VDB advect to move the VDB surface to this position and thus intersect those. Another thing I'd like to do after the VDB analysis, I'm going to drop down a VDB smooth, wire this up in between here, and set our voxel radius to 2 and our iterations to 2. And this is going to smooth the gradient that's used to advect our SDF. And this will get rid of some of those step-like artifacts. So let's highlight our VDB advect, go up 1 level, hit play again. And you can already see that's looking better. However, at a certain step, those cells still will intersect. So let's stop that and go back into the solver. And here's a trick that I discovered by accident, and I'm not quite sure why this trick works. So if anyone has a clue or a decent theory of why this works and why this will actually get rid of those artifacts, please let me know. Okay, here's the trick. Before, I'm going to go into the VDB analysis I will resample my incoming SDF here with a VDB resample node. And this will change the resolution of my incoming VDB. And I'm going to set it to resample my volume using the voxel scale and set my voxel scale to 2. So that will reduce my resolution to half of the original resolution. So basically what we're working with here in this chain is a half resolution version of my incoming VDBs. And when we go up now and let this simulate again, on the one hand this runs a tad bit slower. On the other hand, it prevents my individual cells from intersecting even better than the previous techniques. Also, it makes them look a bit more organic because it smooths them out a bit further. So that is my basic technique for building these cell-like advection structures, such as you've seen in the preview for this whole course. And now what we have to do is build a mesh out of this using the convert VDB SOP, and of course shade, light, and render this. So this is quite an exciting technique, a technique that's really versatile, for example, in fields like medical visualization, where you have these cell structures oftentimes or have this cellular growth, but also for abstract shapes, as in this case. Again, as always, I'm looking forward to what you guys create with that. Please keep sharing your amazing work, and cheers and goodbye.